Hello world, Greg Strike here, and welcome back to The Curious Place. I'm glad you're here. In this video, we're going to be building the bootloader for our homebrew 6502 computer and then using it to load a program directly from cassette tape. I can't wait. One of the things that I love most about the Kansas City Standard was how it finally opened up the ability for people to share data. It wasn't too long after the standard was published that FM broadcast radio stations started incorporating the standard into their broadcasting. Radio listening computer nerds such as ourselves would sit there anxiously waiting with their cassette recorders to hit the record button in order to record the new tones of a brand new program that week. It really was one of the first ways that computer people had to download data. Well, if you've been building this circuit, I've left a little tribute to this practice at the end of my video, so maybe you could load your own 6502 computer with what I've left there. It's just a little something. Let me know if you get it to work. But if you haven't attempted this build yet, have I got some exciting news for you. Our Kansas City Standard circuit is now available as a kit. That's right, guys. Our Kansas City Standard circuit is now available as a kit that you can put together at home with just a soldering iron and some spare time. The kit has serial output, it has parallel output, it has some awesome LEDs, and I think it just looks kind of cool too. So if this is something that you've been interested in and haven't quite had the time to get it together, maybe this is a good option for you. If this is something that you're interested in, head on out to my website, gregorystrike.com, where you'll find a link to my store. I have a small amount of initial stock ready and available to ship. If I sell out and your order comes in, please know that I will make sure to get your order over to you. I hope you guys are excited about these as I am, as I've put a lot of work into it, and I cannot wait to see what you guys come up with. Okay, one last thing. Some of you have been asking for a schematic of the circuit. Well, I ran into some issues when I was converting the breadboard to the PCB for the kit, and I finally have those resolved. Now that I've verified that it's all working, I finally published that schematic available on my website. The kit and the schematic have an extra monostable in it that we didn't cover in the previous videos, but all it does is delay the clearing of the counter. Mr. Monostable to the rescue. So if you'd like and try to build this on your own without the kit, that's now a resource too. And whether you build something from scratch or from the kit, please, I would absolutely love to see what you guys do with it. And I would love it if you posted them in the comments. All right, that should be it. Who's ready to build a bootloader? I know I am. Let's get started. Okay, so here's our circuit, and it's probably apparent that I've replaced the breadboard circuit with our KCS mixtape. It has the monostable timer added to it that I mentioned earlier, and all it does is just adds a delay to the clearing of the counter. If you're interested to see how that's connected, check out the schematic on my website or GitHub or wherever I end up putting that. And the mixtape then connects up to our 6522 VIA that we wired up in a previous video, and everything else is the same. And here's the code from where we left off. In its current form, it reads data from our Kansas City Standard circuit and dumps it to the LCD. If you want to follow along, the code for this project is out on my GitHub page, link in the description. I'm confident that there are better ways to do some of these things that we'll see in the code as I'm making these videos as I learn. So if you see something that's wrong or could be improved, or you just have questions, feel free to drop a comment here on the video or over at my GitHub. I'd love to see them, and it'll help everyone involved. So the first requirement I want to tackle is to give our code the ability to track time. And we're going to use time as one of the ways that we determine whether data has stopped coming in from the tape. So to do that, we'll need a few things. A simple way to do this is to generate an IRQ every X number of seconds or milliseconds, and then use that to increment a variable. Ben Eater has a great video on this, so I'm going to go through the timer stuff rather quickly and cover some of the important things. But if you want a deeper dive, check out his video too. Our 6522 chip has timers built into it, and the timers on this chip are capable of creating interrupts. So, to track time, we basically just need to enable the timer on this 6522 and tell it to create interrupts. And then we write an IRQ function that just increments our variable every single time the IRQ function runs. But wait, we can't just start writing our IRQ statement all willy-nilly, because if you remember correctly, VIA number 2 is also generating interrupts when we receive data from our Kansas City Standard circuit. And the 6502 only knows when a IRQ has fired. It doesn't know which IRQ has fired. So we need to make sure that it knows the difference. So let's get that going. So that means we can remove these here, as we're not going to use them anymore. I also want to remove these comments here, as they don't do anything other than make a mess. So back up here at the top, we want to let the assembler know of some new addresses that we'll be talking to. We'll be using the timer that's in VIA number 1, and it has these 2 bytes here that'll help us configure the timer. And these are located at 6004 and 6005. These 2 addresses together form a 16-bit number that tell the timer how often we want the VIA to create an interrupt. Whatever value we put in here is decremented as the CPU clock ticks, and then when it hits 0, an IRQ is generated. Then we'll let the assembler know about the auxiliary control register here, located at 6000B, and this just lets us configure the mode we want the timer to run in. Basically, we can tell the timer whether we want it to run continuously or just once, and that's what this register is for. And we're also going to set aside 4 bytes of memory here, which we'll call ticks. And we're going to use it as a space to keep track of how often the timer triggers. This is the variable that will increment every time the timer triggers an IRQ. And since we'll know how often our timer triggers, we'll be able to use the number stored in this variable to determine the amount of time that has passed with just some simple math. Cool. So let's jump down here to our reset routine. And this is the code that runs every time the computer is reset. Here, we want to do some initialization that ensures everything is set the way we need it when the computer resets. So first, let's tell VIA number 1 that we want the timer to generate interrupts. To do that, we're going to load this into the accumulator, and then we're going to store it in the interrupt enable register. And if you remember from our last video, if we set the first bit in this byte to a 1, this tells the VIA that we want to enable IRQs that we have flagged in the rest of the byte here. So this bit is flagged here to enable timer 1 interrupts. Then we'll initialize our ticks variable by ensuring that it always starts at 0. So to do that, we load a 0 into the accumulator, and then we'll store that in all 4 bytes of the ticks variable. And then we'll finish setting up our timer. We want it to constantly run, also known as free run mode. So we'll load this into the VIA number 1 auxiliary control register that we defined above. And finally, we're going to tell the VIA how often to generate an interrupt by loading the timer 1 low and the timer 1 high addresses that we defined earlier. I'd like the IRQ to trigger every 10 milliseconds. Since we're using a 1 MHz clock, it would mean every 10,000 clock pulses. But we're actually going to load the number 9,998 here, as this whole process adds an additional 2 clock pulses. So that looks like this. Here's the low byte and here's the high byte. And we're loading them into their registers here. Like I said, we're going through this kind of fast, but check out Ben's video if you'd like more. He really does a good job. But we now have a timer that generates an IRQ every 10 milliseconds. So let's make it do something. So let's look at our IRQ function here, which is called anytime the CPU receives an IRQ request. Here we're handling our data coming in from the KCS circuit, but now we also need to handle a request that could come from our timer. So for now, let's just move our KCS circuit code out of the way, because what we really need to do now is to determine which device caused the IRQ. And the 6522s give us a nice way to do this. Anytime one of the VIAs generates an interrupt, it will set its interrupt flag register, or IFR, to reflect that it has an interrupt that needs to be handled. And since the 6522 has many things on it that can cause interrupts, like timers and ports, the IFR also tells us which part of the 6522 has caused the interrupt. So if we look at what's currently on the IFR from VIA number 1, using a load A here, we now have the state of the IFR in the accumulator. And looking at the data sheet, we can see here that bit 6 represents timer 1, which means if bit 6 is a 1, the timer has generated an IRQ. So if we then use the AND command on the accumulator using the same number, it will essentially mask out anything other than bit 6, turning all the other bits to zeros. So what we would have left in the accumulator will just be bit 6 if the timer has caused an IRQ. So then we can compare that to what we would expect if an IRQ was generated, and then branch if equal to a function that will handle the timer 1 IRQ. And we'll do the same thing here for VIA number 2, but for this one, we're looking for CB1, the port that our KCS circuit is connected to. We'll AND it, compare, and then branch if equal, just like we did the timer. Now in some situations, there's a method that we could use that just uses the bit command and bit 7 of the result to make our decision. We lose some flexibility, but it would have the added benefit of not modifying the accumulator. I like the flexibility and readability of this method, so that's what we're going with here. So let's make sure we create the IRQ function that handles CB1. Since we already have that written, we'll just put it down here. This store A message is something that I never use, so I'm going to remove that. And of course, when it's done, we want it to jump back up to the exit IRQ function, which at this point just calls the RTI, or return from interrupt. The last IRQ piece we need is to handle the IRQ for the timer, so let's create that here. I always like to let the 6522 know as soon as possible that we're handling the IRQ, so we're going to do that first by reading the timer 1 clock low with the bit function, and that should clear the IRQ. The next piece is pretty simple. We just want to increment the ticks variable and all the other bytes if the lower ones roll over. I'm going to do that like this, and we'll increment, we'll branch if not equal, then do the same for all the other 3 bytes. And that's it, and it should now increment every 10 milliseconds. Let's test it. To test it, let's just output a period to the screen every 250 milliseconds. This will tell us that our ticks is ticking and that we've set up our IRQ switching properly. And since we've left our KCS IRQ in there as well, we should be able to play some data through our circuit, and it should write to the screen at the same time. To write the period to the screen every 250 milliseconds, what we want to do is constantly be checking whether or not 250 milliseconds has passed since the last time we printed to the screen. So we'll need another variable to store when a period was last printed. Let's jump back up to the top and create the last print variable here. Remember, our ticks variable is 4 bytes long, so that's why we're at 4 and not at something like 1. The last print variable will just be 1 byte. With that, we'll also want to make sure that last print gets zeroed with our other variables here. And then down here in our loop, we'll check whether or not 250 milliseconds has passed. If so, print a period. For the sake of time, I'm not going to cover it in any great detail, but just know that this code here compares the last time we printed to the ticks variable, and then prints to the screen if 250 milliseconds has lapsed. All right, that should do it. Let's assemble, write it to the ROM, and we'll do our test. All right, that looks pretty good. Okay, so now that we have our timer working, we now need to think about the next piece, which is how to store the program as it comes in from the tape. A program is really just data stored somewhere in memory, so let's set up a place in memory to store it. We'll define that area up here at the top in a variable that we'll creatively call program. But now the question is, where do we want to define it? Let's take another look at our memory map. We have this area up here that's open, so we're going to grab some of that for our needs. We have our 0 page memory here at the top, which is really just the very first part of our address space. It's also a coveted area, as it can be utilized for things that the rest of the address space cannot be, so we're not going to use that, and we'll cover some of that later. And then we have this area here between 100 and 1FF. This is our 6502 stack. The stack addresses are also hardwired in, making them unmovable, so we can't use that. The next open space starts here at 200 and goes all the way over to 4FFF, just before our VIA number 2. So this feels like a good spot. Here I'm going to set aside 2K of RAM that can be used by whatever program we load from tape. So the next spot here at 0A00 is where we will actually store our program, the starting point if I may. So keep 0A00 in mind. We'll need to remember that going forward. We'll use all the space up to 3FFF, which gives us around 13K for our program. That's actually pretty big for our needs, and it actually would take a long time for the 300 baud of the Kansas City standard to fill it up, but we can change this up later if we need more RAM for our programs. But for now, this'll do. So back here in our code, we'll define the program to start at 0A00 here. The next thing I want to do is get rid of the last print variable. We were just using it to test our IRQ. In its place, let's define an area in memory that we can use to track the current state of the bootloader. I'll call this variable bootloader flags, and I don't think we'll need anything larger than 8 bits for what we're doing, so just a single byte should be fine. Up here, I'll make a comment on what the bits are used for, and currently the only thing I can think of that we really need is a way to know whether or not our program has been fully received. And we'll use bit 0 for that, and in the future, if we need to keep track of anything else, we have 7 other bits that we can use. With that in place, let's be sure that we also initialize it so that it always starts at 0 and gets reset along with all of our other things down here. Okay, cool. So another thing we'll need is to keep track of where we are in the receive process. So as a byte comes in, we'll need to know where to write that data in memory. For this, I'd like to define a variable we'll call load pointer here at 05. And since the 6502 uses 16 bits to define addresses, we're actually going to need 2 bytes here. As our program comes in from tape, we'll keep this updated so we always know where to write. With that in place, we better initialize it along with our other variables. However, instead of zeroing it out like we normally would, we actually want to store the location of where our first byte will be written. And in this case, it's 0A00, where we decided to store our program. So let's load the accumulator with the low portion of our program's starting address and store that in the low byte of load pointer, which is the +1. And then we'll load the high portion right into load pointer. The order we store the bytes in here is important because in a moment we're going to have the CPU looking here and it'll expect the bytes to be stored in little endian, which is the least significant byte at the lowest address. So now, down here in our IRQ function, here's the piece of code that's receiving the data from the circuit and then dumping it to the screen. We no longer need it to dump to the screen, so let's get rid of this. And instead, we actually want to store that data in memory. And to do that, we're going to store it using an addressing mode called Indirect Indexed, which is not to be confused with Indexed Indirect, which is a little different, so be careful there. But to use Indirect Indexed mode, we write it out like this using parentheses, which we haven't done yet. So far, we're used to writing it out without parentheses, which tells the CPU to directly write to that area of memory. So if we did this without the parentheses, we'd actually be overwriting the area that we just defined above. But by putting the parentheses around it, we're telling the CPU that we want it to use indexed indirect mode, which rather than writing directly to this location, instead we want the CPU to actually look up the address that we've stored there and then write to the location that it just found. The Y here in this mode actually gives us a way to offset the address after the lookup. So if, let's say, Y was equal to 1, the CPU would just add 1 to whatever address it found. But we're actually not going to use the Y index, so I'm just going to set it to 0. So now that we've stored that byte, we want to make sure that the next byte that comes in doesn't overwrite what we just wrote. So we need to increment our pointer, which will set our pointer to the next place in memory. And that's just as simple as incrementing our load pointer variable. And since load pointer is a 16-bit value, we want to check if we've rolled over. If not, we just want to exit. If we did roll over, then we need to increment the high byte as well. So now, every time we call this IRQ, it grabs the data from our circuit, which clears the IRQ, looks up where to store the data, stores it, and then updates the pointer for the next time we receive data, and then it exits. So with all that, our computer should now be writing data to memory every time it receives something from our circuit. But before we go any further, you know me, I love my sanity checks, so let's test this. Up here in our loop, let's get rid of this test stuff, and instead, let's just read a portion of memory where our program will end up being stored and just print that to the screen. Up here in our reset, let's just store an exclamation mark at that same location. So when this boots up, we'll see a bunch of exclamation marks being printed to the screen. Then, as we play data through our circuit, we should see it eventually get overwritten, which will change what we see on the screen. And that'll help us verify that this portion of our code is working as we expect. All right, cool. Let's assemble and write to ROM, and we'll test. All right, that looks pretty good. All right, we're making some progress. Let's get rid of our test exclamation mark here, and we no longer need it to write to the screen. Now, if you think about what we're doing here, you may have realized that we're doing something kind of crazy. We have this piece of code here that is constantly overwriting memory and moving incrementally throughout our address space onto the next and overwriting more stuff and doing that over and over and over. Well, if we receive enough data, eventually we're going to start writing to a place in memory that we never intended, and who knows what that would do. I mean, we're not going to bring down the power grid or cause the next world war or anything, but it would likely crash our computer. So we need to put some control around this to make sure that this doesn't happen. So if you remember from our memory map, we've reserved 0A00 through 3FFF for our program. Our program first writes the data to memory and then it increments the pointer. So what we want to do is right after it increments, let's check to see if we've crossed the boundaries of what we have reserved. So let's set up this label here, and just after it we'll call it checkEnd. If our pointer is pointing at 3FFF, the last reserved area of our program space, and it gets incremented, the pointer will equal 0400, which comes right after 3FFF. So we really only need to check if we've crossed the boundary after the high byte is changed. So let's move this jump to the bottom here, and then back up here at checkEnd, we'll load 40 into the accumulator, and then compare it to the high byte of our pointer. If it doesn't match, we can exit since we're still within the bounds. However, if it does match, that means we've received the maximum amount of data and we need to stop receiving. So this is where we should update our bootloader flags in order to reflect that we're now done receiving. To do this, we'll load our bootloader flags into the accumulator, which should currently have all zeros in it, so that we can set the last bit to a 1, which is the bit that we're using to reflect when the receive is completed. To do that, we can use OR A like this. Essentially, anywhere we have a 0 will remain at whatever it's currently set to, a 1 or a 0. But where we have the 1s, it'll make sure that those get set to a 1 no matter what it is. So now we can store it back to where we got it from, and the receive bit is now set. But now that it's set, our computer doesn't really know what to do with that flag, so we need to tell it. Once our receive is complete, we no longer need to check if we've received data from our circuit. So to stop doing that, in our IRQ, just before checking the IFR of VIA number 2, let's perform that check. Here we can load our bootloader flags into the accumulator and AND it with this. Doing this will mask out any of the bits that we're not interested in so that we can do a compare on it here. And if we've determined that the last bit is set, let's just exit the IRQ. But if it's not set, we'll go ahead and do a check of VIA number 2 where we can branch just like before. But wait, we can't just exit the IRQ because we need to let the computer know that we've handled it. Otherwise, as soon as we leave the IRQ function, we're going to be sent right back in, which would freeze our computer, because that's just going to happen over and over and over again because we never told the computer that we've cleared the IRQ. So that's why we're branching to this ignore via 2 CB1 IRQ function, which all it does is a bit on port B, which clears the interrupt and then exits by jumping to the exit IRQ. Okay, so this should all be working and it's time for my favorite part, the sanity check. So to do that, let's add some visual feedback to know that we've received data properly. In our IRQ, anytime data is coming in from our KCS circuit, let's just print a period to the display like this. Then, down here, where we've determined that the receive is complete, let's just clear the display and print a D for done. If we see a D, we know that we've set the bootloader flag to 1. The other piece I want to change temporarily is here. Waiting for our KCS circuit to dump 13K would actually take a few minutes. So for testing, I'm going to change this to a 0C. So basically, once we roll over to 0C00, which is 512 bytes, we'll call our receive complete and we'll make the testing a bit faster. Okay, let's assemble. We'll write to ROM and hold on a second. Oh, okay. Looks like I just have an extra colon here. So we'll remove that. And now let's assemble and write to ROM. So let's run a 511 byte file through it, which is 1 byte short of our 512 maximum. We should see a bunch of periods come in as the data transfers. Then, if we send 1 more byte through, the screen should clear and we should see a D show up indicating that it's complete. Cool, that works. So now let's just run a 512 through it, and it should just end with the D. All right, cool. Now let's do 513. It should look the same as before, but we're also testing that our flag is working to prevent further data from coming in, because normally we would see a period at the end because of the extra byte, but we've disabled that when we hit 512 so that it doesn't appear. Cool. Awesome. With that working, let's see if we can make it just a bit more user-friendly. Rather than single characters, let's try to add some strings. To do this, we're going to need a way to write strings to the LCD. I'm going to plop this code right here that's basically the function from back in one of Ben's videos. I modified it to use the Y register and also to utilize a variable called string pointer. So let's hop back up to the top and we'll define that. We'll create that here just after the load pointer, and since load pointer is 2 bytes, we'll put this at 0.7. We're going to use the variable very similarly to the load pointer. It's not going to store our string, but rather it's going to store the location our string is in, and we'll define those below. Anytime our print string function is called, it'll check this pointer to determine the location of what it's supposed to write to the screen. So down here, we'll create 2 strings. One that'll hold the word ready to tell the user that we're ready to receive data, and then one that'll hold the word complete for when we're done receiving data. So let's change the reset function up here to display the ready string on startup. We'll put it right at the end. To do this, we're going to use load A like this, and what this is saying is to grab the low byte of our strReady string address and store it in the accumulator. We can then take that and store it in the low byte of our string pointer, and then we'll do the same, but we'll actually just do it for the high byte of our strReady string. So our string pointer now has the location of our string. From here, we can just call our print string function, which should write it to our screen. Using what we just learned, let's update our load pointer to use the same idea of loading the high and low bytes. What I like about this is it makes it a bit more dynamic, and we can simply update the line at the top of our program to change the location. Okay, one last change before we test. We just need to write our other string to the screen when it's done receiving. We'll do that right here where we are outputting the D. So, doing the same thing as above, we'll load the high and the low bytes of our string to our pointer, but this time we'll use the str complete string, and then we'll dump it to screen. Okay, let's assemble, write to ROM, and we'll test. Okay, well that doesn't look right. Let me take a look here. Okay, I think I found the problem here. It looks like I accidentally loaded these in reverse. Let me move this down here and then we'll assemble and test again. Okay, that looks much better. Alright, we almost have all the pieces. We have a place in memory to store the program, which we're doing. We're using an IRQ to receive the program. We're counting the data to ensure that we don't blow up our computer. And now we just need to figure out how to handle the case that our program isn't exactly whatever the max size is. So we want to be able to load much smaller programs too. If you remember from our first video on this, there's supposed to be like a 30-second header on the tape to avoid any splicing or wrinkling issues at the beginning, but it doesn't really specify a standard way to end the data. It just says here that it ends after the last stop bit. Well, yeah, no kidding, thanks for that. So I think what we can do here is just consider the transfer done if we haven't received a byte in a little bit of time. So to do that, we'll create a variable called lastReceive, and we'll only need 2 bytes of precision. We'll put that address at 09. Now, anytime we receive a byte, we'll update this with the current tick count so that we can compare it later to see how much time has passed. Let's also zero that out here with the rest. To keep our lastReceive byte updated, let's go down here to where we're receiving our byte and save our current ticks value to our lastReceive byte. Since lastReceive is only 2 bytes, we only need to grab the least significant bytes of our ticks variable. And that's actually all we need to do here. Now, up here in our loop, we can subtract lastReceive from ticks, but we really only need to do this on the more significant bytes. The least significant ones will tick by so quickly that it may not even give us enough time. Using more significant bytes will help give us more of a delay from when we received our last byte and when we decide it's complete. And we'll compare that answer to this, which is probably somewhere around 10 seconds. Again, it's just arbitrary. If the answer is less than that, we'll continue our loop. If not, though, some time has passed and we'll make the decision that the receive is complete. And to do that, we'll just set the receive complete bootloader flag just like we did below. And since we'll now have two parts of our code that can determine if the receive is complete, this code here and the maximum file size code, we'll want to turn this into a function. And we'll call that receive complete, which we haven't created yet, so let's do that. And we'll define that here. We'll pull the clearing display and printing code from our IRQ and put it in this function. And for now, when we get here, let's just make this an infinite loop so that our computer will stop when we get here. So both parts of our code now can set the bootloader flag, and all we need to do now is detect that so we can send our program to the new function. So back up in our loop, let's check the flag here, and if it's set, we'll branch to our new receive complete function. Okay, we're almost done, and technically this should all work, but we do have a small problem. Once our computer starts, our ticks will just keep on ticking by, and this code will be comparing last receive, which is 0, to the current tick value, even though we may not have sent any data yet. But it doesn't know that, and once booted, after just a little bit of time passes, it will decide that the program is loaded. So we really only want to run this check here after we've received our first byte. Then we can start checking. To handle this, we're going to grab another bit from our bootloader flags, and we'll use bit 1. Once we've received our first byte indicating that the receive has started, we'll set this to a 1. And we'll do that in our KCS circuit IRQ handler. As soon as we jump in here, we've received a byte. So let's set bit 1 of our bootloader flags indicating that the receive has started. This is done in the same way that we set the flags before, but here we're using bit 1 instead of bit 0. Now there may be a more efficient way to do this because we're going to be running this code every single time we receive a byte. But it works and it doesn't seem to impact performance. So now we know when our receive has started, which means we can go back up to the beginning of our loop and check the bootloader flags to see if receive has started, and if it has, we can run the rest of our loop, but if it hasn't, we'll just keep looping and checking and waiting for it to start. And that should pretty much take care of it, but we do have a few cleanup items. Our IRQ handler is modifying the accumulator and registers, so we really should be preserving these when we enter the IRQ. Placing these at the top of our IRQ will store the X register, the Y register, and the accumulator onto the stack. So then, when we leave, we just do this in reverse, and it preserves all of our registers. The next cleanup I realized is that our print function isn't exiting properly. Once it reaches the end of our string, we're just branching back up to our loop. But we're calling this as a subroutine, so we really need to be sure that we exit it by calling RTS or return from sub. So let's branch it to exit print, and we'll put exit print here. Another thing is as I was testing this off camera, I noticed that our 6522 was generating a ghost interrupt at startup. So we'd always receive a byte of who knows what, and that would get plopped right into memory. So I resolved that issue by first enabling interrupts on the CPU at the end of our reset routine. And we do that by moving CLI down here. The other thing I did was clear any interrupts on VIA number 2 right after its initialization by doing a bit via 2 port B. Alright, one more thing. Since we're so close to being done, let's change this 0C back to 40 so that we can fit the full size in memory. Okay, we're ready for our sanity check. Are you excited? We're getting close. Let's assemble. We'll write to ROM and reset. Okay, that's looking pretty good. I think one more thing I'll do though is add a little delay here right at the end so we can at least see the word completed before we try and launch our program. Okay, wow, we're really close. Okay, really the only thing we have left to make this baby work is to tell the bootloader to start our program. So rather than have this infinite loop here, we're just going to remove that and tell it to jump to the start of our program. Like that's it. Like yeah, that's really it. This should be done. So let's assemble. We'll write to ROM, put it in. Oh, wait, we don't have anything to load yet. Yeah, that's kind of important. All right, let's do that. We'll cover this real quick here. Okay, so I have this tiny little program I threw together, and it's a modification of some of the screenwriting programs that we've seen. It just writes a few things to the screen and does a cheap animation trick at the end. But the big thing here to notice is that we needed to define the origin here to start at 0A00, which is the location that we're storing our programs. Everything from here down gets written right to memory. You'll also notice that I have a few variables defined here that I've put into the area of memory we reserved for our program's use. Also note that I've removed the IRQ stuff from this. We would need to modify our IRQ and do some fancy things if we wanted our programs to be able to handle any IRQs. So I've just left it out of this video. Any IRQs that occur will still be handled by the IRQ functions that we have stored on our ROM. Okay, so with that, I've assembled this and I've converted it to a Kansas City standard encoded WAV file, and then I've recorded it to tape using my old school tape deck from way back in the day. I found that this thing's a lot better at recording than my stupid little handheld recorder. And now we are ready to do our final test. Who's excited? Alright, let's plug this baby in and take a look. Alright, she's playing. She's ready. We're receiving data. This is awesome. Come on. Come on. It's done. Oh my gosh. That's awesome. All right, how about that, guys? It's working. That's awesome. I am so excited. This has been a long time coming. I've put a lot of work into this, and it is so cool to see it all come to completion here at the end. Thank you so much for sticking around with me and watching all these videos. It's been a lot of fun. If this is something that you are interested in seeing more, I have a few other projects up here that I'm thinking about doing. Like and subscribe. You may want to also check out my Patreon if you're interested in supporting me. I think that's it. Oh, if you guys decode any programs with this, I would love to see that. I would love to see any projects you do with this circuit. I love this thing. This has been so much fun. And I think we'll leave it at that. The program is coming right up. And now the moment you've all been waiting for. Bye, guys. Have a good one. Bye.